So today we're going to talk about how the ionosphere is being measured. Okay. So, but before that, let's have a brief recall of what we have discussed last time. So again, let's recall the ionosphere. So the ionosphere is the ionized layer of the upper atmosphere. It has it has four regions. The lowest region is the D region, and then above that would be the E region, and you have your F1 and F2 regions. So typically, the ionosphere can be typically the ionosphere starts from around 80 kilometers above the ground or 80 kilometers altitude until to about around 2,000 to 10,000 kilometers above ground. Okay. So there, no one really knows when or where does the ionosphere really terminate exactly on the top of the atmosphere. But anyway, so most of the ionosphere is where your low Earth orbit satellites are found. Sounding rockets, auroras are also formed in the ionosphere, including air glow and some polar mesospheric clouds. So these polar mesospheric clouds are actually mesospheric phenomenon. No? So in other words, this happens when in the mesosphere. Okay, so just to compare the neutral gases and the electron density. So the ionosphere is labeled or is stratified based on its electron density, whereas the natural gas or the neutral atmosphere is based on temperature gradients. So here you have your troposphere, then your stratosphere, mesosphere, and then you have your thermosphere. So the ionosphere, if you're going to compare that with the neutral atmosphere, the ionosphere is embedded within the mesosphere and thermosphere regions. There are several processes that generate the ions that composes the ionosphere. But the main source of ionization is the process called photoionization, wherein high energetic electromagnetic radiation, usually in the form of extreme UV and X-ray, ionize the constituent neutral gases of the atmosphere, thus forming positively charged ions and your free electrons. That's why the ionosphere is usually defined in terms of the electron density. So that electron density is actually a result of the ionization process, mostly in the form of photoionization. But there are other kinds of ionization, such as rearrangement collision, wherein a neutral gas collides with positively charged ions, thus forming positively charged ions and another set of neutral atoms or atomic gases. We can also have ionization, a reverse version of ionization wherein ions are lost by dissociative recombination. Basically, that's the reverse process of photoionization, wherein your free electrons caused by your photoionizations are interact or combined with positively charged ions, forming neutral atoms. So aside from these processes, we can also have process wherein free electrons can form negative ions by attachment. So that means if you have a molecule like this and an electron attaches to it for some reason, and then this produces a negatively charged ion, okay, wherein that XX electrons give its negative charge. So also negatively charged ions can be detached, on the other hand, via photons via photo detachment. So if a negatively charged ion is struck by photons, therefore that energy coming from that photon will detach the electron, forming a free electron and a neutral atom. Okay, so these are some of the processes that is involved in the formation of the ionosphere. These are the chemical processes. We know that the density of neutral atoms or neutral molecules or neutral gases that is required to form your charged particles in the ionosphere, it varies with density. It varies with time. The density varies with time. So as you go up in the atmosphere, the density of these neutral ions or neutral atoms or neutral gas molecules decreases. Okay. However, because of the source of ionization is majority comes from photons coming from the atmosphere, coming from the sun. So because of absorptions and other several processes like scattering, the amount of ionizing radiation that enters the atmosphere decreases as you go nearer to the surface. So that means, because remember that the ionization requires a neutral gas and a ionization source. So that means there must be some height wherein you have optimum ionization. Okay, so this maximum height is actually depicted in our what we call the Chapman layer. So we already discussed how the Chapman layer is derived, but basically this tells us that the peak ionization are basically functions of chi, which is the zenith angle. So that's the angle between the vertical to the horizontal, as well as to the heights at which these gas molecules are found, because the atmosphere is composed of different gases. You have your molecular oxygen, molecular nitrogen, ozone, etc. So therefore, the corresponding Chapman layers for each molecular gas will basically form the real ionization in the atmosphere or in the ionosphere. Okay, so that's forming, we have your F2, F1, E, D, and sometimes we also have some C layer, which are very, very small electron density. Okay, so as you will notice here that the ionization rates as a function of height also depends on the amount of radiation, not only the amount of radiation coming from the sun, but how that radiation reaches the earth. So therefore, it has a diurnal variation. So daytime, we have a high ionization, and in nighttime, we have low ionization. In fact, okay, the F1 and F2 regions actually combine into a single F layer during nighttime. Okay, and then the D layer is completely removed because of the recombination process, because of the absence of ionizing radiation coming from the sun. And then the E layer weakens in the nighttime as well. So in other words, during the nighttime, the ionosphere is basically composed of two layers. You have your E layer and your F layer, while in the daytime, we have 4 layers to 5 sometimes. You have your D, E, F1, and F2 layers. So F2 and F1 recombined, but even though there is no ionization source in the nighttime, this electron density coming from in the F region in the nighttime is actually due to dissociative ionization or dissociative processes. Okay, so let's have a brief review of what are these layers. So F2 region is the layer that exists from about 220 to about 800 kilometers above the surface of the Earth. Mostly it is composed of O plus atomic ions. Okay, and the maximum electron density varies from about 200, around 300 to 400 kilometers, depending on where you are on your Earth. The E region sorry, the F1 region is located below the F2 region. It's located about 150 to 200 kilometers above the surface of the Earth. As I mentioned earlier, F1 layer merges with the F2 layer, forming one single F layer in the nighttime. Mostly it is composed of molecular ions such as O2 plus and NO plus and atomic ions O plus. So where the F region is the E layer. It's roughly around 90 to 150 kilometers. This is the first layer of the atmosphere of the ionosphere that was discovered, okay, by the Nobel laureate Edward Appleton. So this is the Nobel Prize winner in 1924. In 1947, wherein the Edward Appleton proved the existence of a conducting layer in the Earth's atmosphere. So it's a conducting electrified layer. That's why it's called an E. It's called the E layer. And then the rest of the layers are just labeled alphabetically. Okay. D region is the lowest layer of the ionosphere. It's found about 60 to 90 kilometers above the Earth's surface. It's dominated by the NO plus and O2 plus ions. Okay, and then this tends to increase during winter because of lower zenith angles. On the other hand, it completely disappears during nighttime, where the recombination process is dominant with the absence of your ionization sources. So as you will notice here, there are a lot of dependencies, no, in regards to the electron density of your ionosphere. Okay, so therefore we can actually describe the behavior of the ionosphere based on its variations in space, wherein you can actually see that it has a altitude variation. It also have a geographic location variation. Okay. Also, it also have a spatio-temporal variation because of the Earth's rotation about its axis. So this shows the region, or this illustrates the ionization of the Earth's ionosphere at different locations based on the time of the day. Okay, so this just shows us that when there is the region where there's high ionization, that means that that phase of the sun, that region or that area of the Earth is the one that's facing the sun. Okay. Also, the variations of the ionosphere also varies with time. Okay, so this is your electron density at the F2 region. This is the height of the F2 region. So as you will notice, it is low during nighttime and it is high during daytime. So aside from this, you can also see that there is also spatial dependence on the amount of ionization in the ionosphere, which is basically proves that the zenith angle where the Earth hits where sunlight hits the Earth dictates or behaves or contributes to the amount of ionization. Aside from that, because the main source of ionization is the sun, so that means whatever major changes happens in the sun, therefore it also has an effect to the Earth's ionospheric ionization. Okay, so this is an example of the variation of your total electron content, okay, relative to solar irradiance as well as your geomagnetic activity. So how do we probe the ionosphere? And so when we sense the ionosphere, we can actually sense them two ways. You can sense them by actually measuring them. We call that in situ. So that means in situ means in situation. So usually we use Langmuir probes on sounding rockets and low Earth orbits. So this is the most exact way to determine the electron density because you're actually measuring the electron density directly. On the other hand, we can also measure the ionosphere remotely. So there are different ways to remotely sense the ionosphere. The first of which is the remote sensing by radio sounding. So in this case, we send radio signals to the ionosphere, and we collect what is reflected back by the ionosphere, and from the frequency as well as the time of arrival, we can know the where this plasma are relative to the surface of the Earth. So we call that radio sounding. We can also do you can also measure the ionosphere based on how it is being delayed or refracted by the ionosphere. Okay, so in this case, we use satellite to ground, and sometimes we also use satellite to satellite propagation. Okay, and also we could also observe the ionosphere using optical techniques. Okay, so let's say all sky cameras are usually used to observe the ionospheres, most specifically variations or transient variations in the ionosphere, such as medium scale traveling ionospheric disturbances and all sorts of those things. Okay, but in today's class, we're going to focus on three ways to probe the sun. So using ionosonde, so this that's an HF radar, so high frequency radar. We also going to introduce to you concept of satellite to ground, as well as satellite to satellites sensing of the ionosphere. Okay, so let's start. No, for remote radio sounding and remote radio occultation, we have to first realize or appreciate that in the radio wave spectrum, the radio wave spectrum is actually divided into different subbands. So you have your extreme low frequency, that's ELF. Then you have your VLF, VF, VLF, LF, F, MF, HF, VHF, UHF, SHF, and EHF. Okay, so these are usually divided in terms of how they behave as they are propagating through the ionosphere. So how do we mean by that? So basically the ionosphere, because it is composed of electrically charged particle, that means the ionosphere is dispersive. Okay, the ionosphere is dispersive in the radio waves. So that means different wavelengths or different frequencies in the radio wave bands will behave differently as it encounters the charged particles located in the ionosphere. And we use this concept to know how we could be able to measure the ionosphere using these frequencies. So for example, if we send signals at the lower frequency bands or longer wavelength bands, like for example, HF, MF, until ELF, at these frequencies, okay, the ionosphere is basically reflective. In other words, the ionosphere behaves as a mirror. On the other hand, if you're going to go higher than HF, VHF, UHF, the ones that we use for TVs, HFS, EHF, as well as the other bands, higher frequency bands, these frequency bands or these radio wave bands actually pass through the ionosphere. Some of them are refracted more than the others. Okay, so for example, if I send AM radio from a transmitter, because AM basically has a lower frequency band. Okay, so these AM waves are reflected by the Earth's ionosphere. Therefore, AM waves or AM frequencies can actually travel longer distances across the ground. So we call this your sky wave. Now, for higher radio waves, frequency like TV waves and FM waves, they can actually pass through the ionosphere. That's why satellite TV can be used. So again, let's recall, these are the different layers of the ionosphere. So one of the main parameters that we use to characterize the ionosphere are the are the peak density at each layer. So we have your NMF2, that's the maximum electron density or maximum electron density at the F2 region, and it is found at the HMF2. So HMF2 is the heights where maximum ionization in the F2 region occur. So we are going to use this parameter. Of course, these are the two main parameters when we describe the ionosphere. But we can also describe the ionosphere using its NMF1, HMF1, NME, HME, and these parameters are usually measured using ionosondes, radio occultations, and sounding rockets. So let's start with ionosonde. So as I mentioned earlier, ionosonde is basically a radar. So what happens here is that uh, an ionosonde transmits pulses of radio waves that is transmitted to the ionosphere, and then the ionosphere will reflect these pulses, and from the time of arrival, we can know where the ionosphere is. Okay, but because, as I mentioned earlier, the ionosphere is dispersive in the radio wave, so that means different frequency will be reflected by the ionosphere at different heights depending on the electron density. So what happens here is that the ionosphere sends ranges of frequencies or ranges of radio waves usually from within the high frequency band. So that's about 1 megahertz to about 10 megahertz maximum. Okay, and then the resulting pulses or the resulting signal is traced as a function of height and frequency. Okay, so these are what we call your traces, and these traces is called the ionogram. So the ionogram is the resulting uh, data coming from ionosondes. Okay, so from the traces, you can actually find the parameters that I previously mentioned. Okay, so what happens here is that when charged particles in the plasma environment like ionosphere is dispersive in the radio waves, so in other words, the refractive index of the ionosphere is dependent on the electron density. In fact, the higher the electron density, the higher the refractive index. Also, the refractive index varies inversely with the frequency of being transmitted. So what does it mean? It means that if you have lower frequency, that means the refractive index is higher for that specific frequency. So that means lower frequency can be easily be reflected through the process of total internal reflection by the ionosphere. So as I mentioned earlier, around more than 550 megahertz or more, the ionosphere is refractive. So that means that these radio waves can pass through. But the ionosonde uses high frequency bands, so around 0.1 to 30 megahertz. So wherein the ionosphere is reflective. At these frequencies, we use the total internal reflection principle, which you already know by heart. Okay. So as the frequency increases, each wave is refracted less by the ionization, because remember that as you go high, what we can actually, as you go high, the altitude electron density increases. Therefore, refractive index increases, but the frequency of transmission will be decreased. So, but the end result is this, no? For example, here, okay, for low frequency waves, it is easily reflected. So at lower heights, it can already be reflected. And then as you go higher, uh, the higher parts or the more ionized regions of the ionosphere is the one that reflects. So what happens is that the frequency of your transmission actually matches the critical or the plasma frequency. Okay, the plasma frequency of the ionosphere. Okay, so the end result is that you're going to have this kind of trace. And from this trace, you can actually calculate the electron density. Now, please take note that what happens here is that if the ionosonde transmit data vertical, it is reflected back like this. So if you're going to calculate the time of arrival, what is actually being observed or perceived by the measurements is that the ionosphere, the part where the part of the ionosphere that reflects these radio waves is somewhere here. So we call this the virtual reflection heights, or simply the virtual heights. But in reality, the propagation direction is actually curved like this. So the actual reflection height is actually lower than the virtual heights. So what the ionogram actually provides us is the virtual heights, and then using complicated conversion techniques, the virtual heights is converted to actual heights. Okay, so how do we interpret ionograms? So this is an example of an ionogram. So you have your O wave or ordinary wave. So this is the actual reflection of the waves. And then you have your additional wave, or sometimes or commonly known as your extraordinary wave or X wave. Okay, so this X wave occurred because of the additional contributions of the magnetic field into the reflection process. But what's important for ionograms is the O wave. So from these traces, okay, this type of ionosonde automatically estimates the electron density. So this is the electron density. So this electron density profile is derived from the ionospheric parameters derived from the ionosonde. So how do we interpret this O wave? And sometimes X wave. So this is a typical interpretation of an ionogram. Okay, so applying this, what we have here is that this will be your FOF2. So FOF2 is the critical frequency of the ordinary wave reflected from the F layer. So that means at around 5.5 megahertz, okay, that's the maximum frequency that the ionosphere reflected, and it corresponds to the maximum electron density of the ionosphere during this time. Okay, and then this dip, so this curve has a dip here like this one. So we call this your H prime F2. So this is the virtual heights of the F2 layer. Okay, so as I mentioned earlier, the virtual height is generally higher than the real height. So this ionosonde automatically calculated the real height, no? So the real height is somewhere here. So this is what we call the HMF2. And that is lower than the virtual heights. Okay. Now next would be your F1 layer. So FOF1 is actually found here. So that means the critical frequency in the F1 layer or FOF1 is actually found at around 4 megahertz. And the virtual height of the F1 region is found here. Okay, so this corresponds to this and this. And lastly, the E region, you can actually find the E region. So FOE is the critical frequency of the ordinary wave at the E layer. So it can be found here, and the height of the FOE layer is somewhere here. So it's similar there. Of course, there are additional signatures that can be found in a typical ionogram, but we're going to discuss that a little bit later. Okay, so as I mentioned earlier, the frequency of transmission is directly proportional to the amount of electron density or ionization. So a simple equation is used to convert the critical frequency at the F2 layer, FOF2 in hertz, into electron density, maximum electron density of the F2 layer. So this is a very simple but very useful conversion equation. So from the FO2 region, okay, from the F2 critical frequency of the F2 region, FOF2, we can know the or estimate the electron density at the F2 layer. So that's why this electron density profile, so this is FOF2, this is the peak density. Okay, so again, as I mentioned earlier, the actual height is basically lower than the virtual heights. Questions so far?
Sir, ako po, may tanong po.
Sige. Quick question lang,
Y-
quick question. Sige.
Apo, yung FOF2, ay ano po yung dito po sa graph sa left? Ano po yung x-axis, di ba po? Hertz frequency?
X-axis is in
Megahertz.
frequency, megahertz, yes.
Typical value po ba yan? Actual, ano yan?
It depends on where
Kasi
you are.
iba po yung value dun sa right.
This one
I
here,
mean,
right?
yung graph po sa right, ako po yan. Yung positions ng
This is just an example.
mga peaks.
This is just
Okay.
a parang typical, no? But the amount of ionization, as I mentioned before, earlier or during the recall, it is actually a function of where you are on Earth. So this is in Millstone Hill in Massachusetts. So this is in a mid-latitude region. So the ionization in the mid-latitude region is lower than the equatorial region. So if we're going to look at the equatorial region, the FOF is actually more than 5.5 megahertz.
Okay po, sir. Thank you po.
Okay. Later, I will show you some additional examples now. Okay. So this is what a typical ionogram looks like now. So usually using this Lowell Digitron data, they have automatically separate the O wave and the X wave. And these parameters are actually calculated automatically. Okay, but however, these measurements are just first level measurements. Okay, the best way to really calculate or estimate this ionospheric parameters is by manual scaling. Okay, manual scaling would still be the most accurate, but it's very tedious to do. Okay, now, so this is your typical ionogram. This is a very normal ionogram, and this will give you a very normal ionosphere. But there are transient features in the ionogram that you can actually observe from now and then. No? So one of the most common is what we call the sporadic E. Okay, the sporadic E is actually a intense cloud of ionization found in the E region, and it happens sporadically. So very transient and very unpredictable. Okay, so in the ionogram, it looks like this. Okay, so this is your ionogram. This is the sporadic E signature in an ionogram. Okay, sometimes this sporadic E is so strong that even for higher frequencies, okay, the E region or the sporadic E layer actually reflects all of it. Therefore, no F layer can be traced or can be detected from the ionogram. Okay, this is another example of that. So this is coming from Merlin's recent publication. So you have your ionospheric signal. So this is your F2, F1. Sometimes you have F3, but this is your ES region. Okay, so what happens here is that if there's a sporadic E because of the high ionization, very high than usual, okay, it actually, the ionization rate there, ionization electron density there in the sporadic E layer actually rivals in terms of magnitude, no? Compared to your F2 region. So sometimes if there's a strong sporadic E layer, as I mentioned before, for ionograms, the F layer cannot be traced anymore. Okay, and if in real life, if the sporadic E layer happens, that means if usually this certain frequency can penetrate the E layer, reaching to the F layer, thereby reaching this place where this transmitted radio wave is intended to go to. What happens is that if there is a sporadic E, the same frequency will not reach this area. So it will be prematurely reflected at the E layer. Therefore, this will be received by someone here and not here, which is the first intention. So sporadic E layer is actually very important when it comes to radio propagation, especially when you're considering or studying sky waves, etc. Okay, so that's your sporadic E layer. Another transient features in an ionogram is what we call the spread F. So as the name suggests, it is the spreading of the F layer signature. Okay, so this is an example of that. So this is your F layer, and then above the F layer, there are spreading in the echo. So this is actually a result of the presence of irregularities in the ionosphere. Okay, so if there are irregularities in the ionosphere, therefore they can affect the propagation of radio waves, especially from those trans-ionospheric propagation, or we say trans-ionospheric, those frequencies that pass through, not reflected by the ionosphere. Okay, so if there's a presence of spread F, so what happens is that, okay, there are irregularities, or sometimes we call that plasma bubbles, sometimes we call that plasma plumes, depending on the structure of these irregularities. But what happens is that if there is a spread F events in the F layer, signal transmitted through the F layer can be scattered by the spread F at different towards different locations. Okay, so instead of having one point of destination, spread F actually makes it hard to detect, okay, this signal. So that's one of the consequences. Another consequence of spread F events is that for trans-ionospheric signals, radio scintillation or ionospheric scintillation may happen. Okay, so what if you are going to use, let's say, GPS, and spread F occurs in the ionogram, so chances are there will be some reception issues for GPS receivers, which may affect the performance of such um, equipment. Okay, so that's the sporadic E and the spread F. Now, uh, so from the ionogram, we can actually observe or calculate how the maximum density at the F2 layer and the height of the F2 layer varies with time. So as I already mentioned earlier, during daytime, NMF2 is expected to be higher, but at lower altitudes. But in the nighttime, it is expected to have higher heights but lower ionization or electron density. So with your question earlier, the this is in NMF2, no. So higher latitudes, around mid latitudes, the NMF2 is low. Lower altitudes, usually towards the low latitude regions, the ionization is higher. Okay, so this graph from Hu et al. In 2014 shows the NMF2 and HMF2 using ionosonde, that's the blue one, and using another kind of technique or another technique to measure the NMF2 and HMF2. We call that your radio occultation technique. Specifically in this paper, they use the cosmic program or cosmic satellites. Okay, so cosmic satellites uses a technique called radio occultation. So radio occultation uses satellite to satellite propagation, and through the refraction of the signals, okay, through the bending of the signals as these radio waves pass through the ionosphere and the atmosphere, we can actually derive the electron density as well as your temperature profile for your neutral atmosphere. But for our purposes, we're going to focus on the electron density. So what happens here is that this satellite, this low Earth orbit satellite, has a GPS receiver. So it receives GPS signals from GPS satellites or other GNSS satellites or global navigation satellite systems. So as this low Earth orbit orbits the Earth, so let's say at this point, since the signal already passes through a thin amount of the ionosphere, so this radio wave is refracted or bent slightly. But as this satellite goes in this direction, so more and more of the radio waves is being refracted. And from the refraction, we can get the refractivity of the ionosphere at certain heights. And from the refractivity, we can estimate the electron density. So from the electron density provided by the radio occultation technique, we can also find or determine the NMF2 and HMF2. Okay, in fact, for cosmic for this radio occultation techniques, HMF2 and NMF2 is the one that is mostly used parameter. So this is an example of the actual electron density profile determined from your radio occultation. So this happened in two different dates. October 14 will be the black, and December 11 would be the red. So from here, we can estimate the NMF to HMF2 in December and in October. And if you're going to combine all of this, okay, you can come up with this graph. So this is graph provided by Professor Liu in 2015, wherein he mapped the NMF2 in geographic locations, HMF2 in the geographic locations, as well as the altitude, latitude profile of your electron density. So from here, we can actually observe the phenomenon called the equatorial ionization anomaly, which is a very common or which is a unique feature of the ionosphere in the low latitude equatorial region, where the Philippines currently resides. So far, we've talked about NMF2 and HMF2 obtained using ionosondes and radio occultation. Now, aside from NMF2 and HMF2, another parameter is being used to describe the level of ionization in the ionosphere. We call that the total electron content. So basically, the total electron content, as I mentioned before, is the sum of the electron density from the bottom of the ionosphere to the top of the ionosphere in a 1 square meter or 1 square meter area. Okay, so what happens here is that, so from this point to this point, we just add all the electron densities from this point, from the top, this should be top. So from the bottom to top, we call that your total electron content through this column. Okay, but if the column is on the vertical direction or the zenith direction, we call that a special name. We call that the vertical total electron contents. So that's the total content from the bottom to top. Okay, and total electron content is usually measured in terms of total electron content units, or TECU, or tech units, which is equal to 10 to the 16 electrons per square meters. Okay, so that's it, no? That's your total electron content. Okay, so what we usually do is that if we do not have an electron density profile, therefore we cannot do this integration. But we can actually still estimate the total electron contents using some form of a workaround. Okay, so as I mentioned earlier, the refractive index is related to the electron density. Okay, so that means the delay that is caused by the refraction can be used to estimate the amount of electron density and therefore the total electron content, or directly to be total electron content. And that is what we usually use in our group. So that workaround uses the signal delay coming from signals. So for example, you have a GPS signal here, a GPS satellite, and it sends signal through the ionosphere toward to the surface of the Earth. If we know what to expect, okay, the time of arrival from the GPS satellite to the ground, but we know what we actually measured, then we can actually estimate the signal delay. Okay, and that signal delay is related to the total electron content by this equation. So approximately it is equal to the delay in due to the ionospheric refraction is approximately equal to 40.3 times tech, or TEC, divided by f squared. So this, as you will notice here, that the delay, or the amount of refracted ray through as described by your signal delay also depends on the frequency. Okay, and usually we use the global navigation satellite system. Sometimes we use the GPS to estimate this. So the slant total electron content, so that's the total electron content through the path of signal from the GPS satellite to the receiver, can be estimated using this equation. Okay, so basically what we're doing here is differencing the delay at two frequencies in the L1 and L2 bands of your GPS. L1 band has a frequency of 1.5 megahertz. L2 band has a frequency of 1.2 megahertz. Sorry, again, so L1 band has a frequency of 1.5 megahertz, and L2 band has a frequency of 1.2. Sorry, again. So the full frequency of the GPS L1 band is 1.5 gigahertz, and L2 band is 1.2 gigahertz. And then the raw L2 and L1 are the perceived distance between the satellites and the receiver by measuring the time of delay. Okay, so from here we can estimate the slant's total electron content. But what's more important to us is what we call the vertical total electron contents. So the vertical total electron content, or VTEC, is estimated using a thin layer model to be just a component of the slant total electron content along the vertical. Okay, so we just use a mapping function, a simple cosine function at this point. We call this the ionospheric piercing points. Okay, so this is the intersection between the thin layer that we assume and the signal path. So at this point, we can estimate the vertical total electron content from the slant total electron content using the mapping function, wherein the Z prime is the zenith angle at the ionospheric piercing point, while Z is the zenith angle at the receiver location. So using this equation, we can estimate the vertical total electron contents from your GPS signals. And this is the undergraduate thesis of Merlin. Okay, so if we're going to assume that the layer is like this, so this is your slant total electron content and your vertical total electron contents. So usually, the receiver receives signals from a lot of satellites. Before, it can receive up to 8 satellites, but right now it can actually receive up to 20 satellites because of the increased number of satellite systems other than GPS. So we already have GLONASS, we already have Galileo, Beidou, etc. No? But the important thing to remember here is that each satellite receiver pair will give you a different slant TEC. So if you have a different slant TEC, therefore you have different vertical total electron content. Okay, so what happens is that the receiver will have a lot of slant TEC and vertical total electron content, or VTEC. So what happens is that to estimate the vertical total electron content on the receiver's location, we use a weighting average, or we average this vertical total electron contents with more weights given to those zenith angles that are very small, or in other words, those satellites that are near the overhead of the receiver. Okay, so this is described by this image. So this image shows the vertical total electron content of all satellites seen by our receiver located in the Quezon City. And then the black one would be the weighted average of the total electron content. So as you will notice here, the x-axis is the UTC. Okay, so this is universal time. 0 UT is 8 a.m. 12 UT is 8 p.m. So as expected, during daytime, the ionization is high, therefore the total electron content is high. And during nighttime, the total electron content is low. Okay, so this is in uh, uh, Quezon City, a receiver from Quezon City around 2 months ago, okay, August 27, 2021. Last, 2 years ago, February 2019, this is another example of your total electron content measured from the same, using the same receiver. So as you will notice here that the peak electron content, or peak TEC, is about 40 to 45 tech units. Okay, this is in 2021. But in 2019, it's only about 20 to 25. Okay, so it's about almost half as much as right now, no? And that is due to the fact that in 2019, the solar activity is low, and this year the solar activity is picking up. So that demonstrates the dependence of solar activity to the amount of ionization in the ionosphere. Okay, so this is only for 1 point. So let's label four instances, or 4 time stamps. Okay, 0 UT, 6 UT, 12 UT, and 18 UT. So A is 0 UT, B is 6 UT, 12 is 12 UT is C, and 18 UT is D. Now we can actually express the total electron content in a map. We call that your global TEC map, and that map is based on TEC measurements from GPS satellites, GPS receivers located around the world. So by collecting everything, all the profiles in all available stations for specific time, we can come up with a regional TEC and a global TEC. So this square is actually this square. So this is your regional TEC map, and this is your global TEC map. So for letter A, you can see that the ionization is low. B, you can see that it's maximum. And then C, it's getting lower than B. And then letter D, it's almost it's very very low. Okay, so this demonstrates the spatio-temporal variation of your total electron content. And if you want to animate that, we will end up with this equation, with this figure. So as you will notice that because ionosphere is basically made up of plasma, therefore, aside from its behavior according to the time of the day, it will also behave according to the configuration of the magnetic field lines. So that's why as the Earth rotates, the region where the ionosphere has a high intensity or high electron density or TEC, that those region follow this curve line. So this curve line, as we discussed a few weeks ago or a few days ago, this line follows the line where you have zero inclination angle in the magnetic dip angle, or in other words, this is what we call your geomagnetic equator. Okay, so one important feature here is that the geomagnetic equator is actually passes through the Philippines, not in Indonesia. And then northern Philippines is actually part of what we call the low latitude region. So if you're going to notice here that the Philippines is actually located in two different regions, equatorial region and low latitude region. And what's important is that the northern part of the Philippines is where the north crest of the equatorial ionization anomaly is found, and the lower part of the Philippines is where the equatorial region is found. Okay, so that's your variations in the ionosphere for both and uh, temporal and geographical or spatial. So as I mentioned last week or last time, other variations of the ionosphere can be determined. The ionosphere global total electron content varies with solar activity as well as with geomagnetic activity. So what we've talked about today is the general behavior of the ionosphere and how we measure this important parameters, the NMF2, HMF2, and the total electron content. And we have to know how to uh, precisely measure this as best as we can, because we need these parameters to know how space weather affects us on the ground. And that will be our next lesson next week, or next topic, no? Which is what we call the space weather effects. So the space weather effects actually has a very important connection with the ionosphere. So whatever happens in the space environment, there is direct effects on certain applications. Of course, you have your atmospheric effects like your aurora. Also, we also have if there's a transient energy coming from the sun like CMEs or solar flares or solar energetic particles or sometimes cosmic rays, they affect not only the assets we have in space, like in satellites due to radiation damage, single event upsets, um, what do you call this, orbit decay, etc. It also has an effect on the ionosphere. And if something happens in the ionosphere, all uh, all or yeah, most technologies that depend on radio wave propagation may be affected as well, such as, for example, positioning issues when it comes to navigation, also disruption in satellite reception. Okay. If there is also, we already discussed this before, no? If there is a geomagnetic disturbance in the Earth's magnetic field caused by, let's say, CMEs, or let's say fast-moving solar winds, the magnetic field is disturbed. Therefore, it may affect power systems due to induced currents in the wires. Okay, so these are some of the space weather impacts, no, to human lives. They may be indirect, but still important to study. So that's all for now. Bye bye.